The total time it takes to tape out a semiconductor design is governed by a strict mathematical sum. It is the time spent on the design itself, plus the required computation, plus infrastructure delays, rework, and final governance. To compress that schedule today, the highest leverage target is the infrastructure variable. The actual design and governance stages are bound by human engineering limits. The industry currently focuses massive resources on accelerating EDA algorithms, utilizing AI and hardware acceleration to speed up logic simulation and physical implementation. But those optimized algorithms run on top of an uncoordinated substrate. A blazingly fast placement engine still halts if it is waiting in a queue, waiting for a software license, or waiting on a saturated network file system to deliver its data. We call this cumulative delay the infrastructure tax. It is the addressable schedule burn caused strictly by queuing logic, metadata stalling, license starvation, and network merges breaking under load. To shrink the critical path to tape-out, we have to decouple the design semantics from the infrastructure execution. This is achieved using a predictive tensor control plane, or PTCP. Investing in faster individual algorithms yields diminishing returns if the underlying compute cluster, storage, and network remain a passive, uncoordinated bottleneck. This diagram illustrates a standard tape-out pipeline. You can see the sequential stages from RTL and IP integration on the left, running all the way through physical verification and final GDS or OASIS delivery on the right. Inside each of these discrete rectangular nodes, the execution time is highly optimized by the specific EDA vendor's tools. However, the red arrows indicate iterative closure feedback, engineering change orders, timing violations, and rule deck findings. Every time a design loops back, the wait times between these stages compound. A 10-minute delay waiting for a license across thousands of parallel regression tests can push a sign-off merge into the next operational shift. Beneath the standard pipeline, we introduce the PTCP, Cross-Layer Control Overlay. This system underpins the entire workflow. PTCP directly interfaces with your existing infrastructure, coordinating compute placement, license admission, network pathing, and storage data locality. There is a strict boundary here. PTCP governs the infrastructure substrate. It never touches the design truth. Quality of results, sign-off rules, and algorithmic convergence remain entirely authoritative to the EDA tools. By converting a passive collection of servers and storage into a predictive execution fabric, engineering teams can protect the tape-out critical path from compounding iteration delays. Electronic design automation is not a single uniform workload. Every stage of the pipeline presents a distinctly different demand profile, known as a resource signature. Consider RTL regression testing. Its signature is fleet computing, thousands of test jobs gated by your software license pool. Contrast that with physical design, requiring massive single-node memory. Finally, physical verification, like DRC and LVS, creates severe network congestion. Traditional workload managers, like IBM LSF or Slurm, are blind to these complex signatures. They operate on basic logic, matching requested host capabilities to available execution slots. A traditional scheduler will happily launch 10,000 parallel jobs into a cluster, even if the shared file system's metadata server is already saturated, causing every job to stall on basic read commands. Similarly, the scheduler cannot tell if a network path is heavily dropping packets before it places a highly distributed, merge-heavy workload across the spine. Optimizing your compute placement yields zero tape-out velocity if the surrounding data storage and network fabric are quietly suffocating the application. This schematic details the functional architecture of PTCP. It bridges the gap between EDA workflow intent and physical infrastructure execution. At the top is the observation plane. PTCP ingests telemetry from flow schedulers, license managers, storage layer, and network fabric. This observation relies strictly on metadata, correlating job states and queue lengths without invasive deep packet inspection. Telemetry then flows into the predictive slow path, where the system forecasts resource demand and proposes candidate actions to optimize the workflow. For instance, the slow path might recommend pre-staging a data cache or delay job admission to prevent a metadata storm. Before action is taken, proposals must pass through the policy and integrity gate, the central defense mechanism protecting the physical design. The integrity gate automatically rejects any proposed infrastructure action that could violate foundry sign-off constraints, quality of results invariance, or contractual license entitlements. Once a policy is approved, it is handed off to the deterministic fast path for immediate actuation. The fast path enforces these rules using existing certified IT standards. It programs the approved intent via Linux AF_XDP for packet pacing, or uses sonic switch APIs to guarantee network isolation without proprietary hardware lock-in. PTCP does not replace your physical network or core job scheduler. It acts as an overlay, passing mathematically bounded intent down to those existing systems. Finally, the system operates on a closed-loop safety fallback. If telemetry goes stale or a physical switch fails, the PTCP policies automatically expire, and the cluster immediately reverts to its certified default scheduler behavior. By splitting the architecture into a slow, predictive planning brain and a lightning-fast enforcer, you accelerate the substrate without ever putting sign-off safety at risk. The control problem escalates with AI-driven agentic EDA tools. These platforms autonomously generate, launch, and evaluate thousands of rapid design space experiments in parallel. This hyperproductivity often creates an immediate infrastructure shock. The rapid fan-out of autonomous jobs causes massive simultaneous cache misses, drains expensive license pools in seconds, and throws the cluster into gridlock. Deploying these agents safely requires PTCP to act as an infrastructure governor, enforcing strict budgets on concurrent trials based on what the network and storage can actually physically support. PTCP also provides automated topology containment. If a speculative AI design branch fails a hard quality of results limit, the control plane immediately cancels any orphan downstream jobs, instantly freeing those locked resources for the critical path. Agentic AI expands the volume of design iterations an engineering team can initiate, but without a strict infrastructure control plane, a faster AI simply generates network congestion at a higher velocity. Evaluating the return on investment for PTCP requires strict mathematical bounds. Guided by Amdahl's law, the maximum schedule reduction is strictly limited to the portion of the tape-out time actually caused by addressable infrastructure delays. This chart models the illustrative sensitivity of end-to-end schedule reduction against that addressable delay. Look at the x-axis. We first measure the customer's production flow to identify the exact percentage of the schedule consumed purely by infrastructure waiting. Assume 20%. If infrastructure accounts for 20% of the total delay, and PTCP successfully eliminates 40% of that specific delay, tracking up to the middle curve shows a direct end-to-end schedule reduction of 8%. Precision measurement of this addressable baseline is mandatory. You must establish this foundational variable before calculating the enterprise value of recovered engineering hours or avoided compute costs. Because quality of results is invariant and tape-out deadlines are mission-critical, no sane methodology team will deploy an automated control plane blindly across their cluster. This diagram outlines a pragmatic, four-stage, evidence-gated adoption roadmap designed to honor risk aversion. The process begins with the baseline and shadow phases across the first 90 days. PTCP only ingests telemetry here, producing counterfactual predictions to prove its accuracy. Next is the canary phase. Here, highly reversible actions like job pacing and data pre-staging are applied exclusively to a partitioned, non-sign-off regression farm. Advancing past this stage requires absolute, documented proof of identical test seeds, exact coverage equivalence, and flawless one-command rollback capabilities. Finally, in the scale phase, control is cautiously expanded to highly sensitive workflows, like physical design and multi-corner static timing analysis. This scale is only maintained as long as the continuous evidence of determinism remains intact. Any change to the tool release or rule deck forces an automatic recertification. Tape-out schedules no longer need to bleed days into uncoordinated wait times. By treating your compute, licenses, network, and storage as a single, actively coordinated system, engineering teams can compress the critical path, preserve their design intent, and achieve safer, faster tape-outs.